You basically flip it. If you have a negative exponent, you just take that power and you flip it to,
Oh, okay.
yeah. So this is 1 over 4 squared.
1 over 16.
Which is 1 over 16. So what is the y? 1 over 16. So how about when x is -1?
Just 1 over 4.
You got it?
Oh, let's go.
How about when x is 0? What's
0?
4 to the 0? Nope, you just told me. What's 4 to the 0? What's anything to the 0 power?
1?
It's 1.
Oh.
And what's 4 to the first power?
4.
And what's 4 to the second power?
16.
Good. Now they're probably going to
Let's
ask
go.
us to graph it.
Yes, it says choose the correct graph, and then it's got a bunch of graphs.
So look at
I just
this.
have to look for the.
Let's take a look at this graph real quick. At -2, -1, 0, 1, 2. Okay.
Okay.
What is the y value when x is -2? What's the y value?
1/16.
It's 1/16, which is barely above 0, right?
Mm-hmm.
How about when y equals, or when x equals -1? What's the y value?
1/4.
Good, which is a fourth of the way to 1. How about when x equals 0? What's the y value?
1.
And how about when x equals 1? What's the y value?
4.
Do you see what's happening?
Yeah.
How about
and
when
then
x
it's
equals
gonna go
2?
to 16.
It's way up here. So this is what a graph, an exponential graph looks like. It goes
Mhm.
through 0, 1, and then it goes exponentially up like that.
Yeah.
That's what an exponential graph looks like in general when your
Yeah.
base is bigger than 1.
Okay.
Because it doesn't matter what it is, it's always going to go through 0, 1,
Mm-hmm.
right? And it's always going to approach your x-axis but never reach it. As long as you've got some number to the x, as long as this number right here is bigger than 1, that's what the general shape of that graph is going to look like.
Yeah.
You have a horizontal asymptote at the x-axis, and it goes up exponentially to the right. Okay.
Mm-hmm. All right, I can put another one in there because there's another one similar to this. Except this time, it's with a fraction.
Okay. Now with a fraction, it's going to flip it.
Okay.
So now do you see the difference here? The difference is that the base, remember I told you as long as the base is bigger than 1, it's going to look like that on the last page. Well, this base isn't bigger than 1. This base is smaller than 1.
Yeah.
So what's going to happen is, I'll tell you and then I'll show you. It's going to flip it like this.
Yeah.
That's basically what's going to happen.
Yeah.
But if you do the math on it, ready? Watch this. What's 3/4? 3/4 to the -2. You remember what I talked about with the negative exponent? You could also just flip what's inside. It's 4/3 to the +2.
Mm.
That's one of those tricks I showed you. A over B to the n, sorry, to the negative n, equals B over A to the +n.
Okay.
You just flip them both. It's called the Dwyer property.
The Dwyer property. Wow.
I've never seen it named ever before, so I just claimed it once years ago.
That's a good idea.
Yeah. I don't know if anyone else picked up on it, but I did. So this equals 16 over 9. Right?
Okay, yeah.
16 over 9. Okay, how about this one right here? If you have 3/4 to the -1, tell me what that's going to be. Use the Dwyer property.
4/3.
Let's go.
Yes. First
See, it
try.
works great, that Dwyer property.
Wait,
And what's
I know the next one. I know the next one.
Yeah, what is it?
1.
Let's go.
Yes.
What's the next one?
3/4.
And what's the next one?
9/16.
Uh-huh.
Yes.
All right. So look at what
Oh,
happened
that's
on our
cool.
graph.
It's like reverse.
That's right.
Side.
Look what happened on our graph.
That's
If
actually
you're going
kinda...
to the left, it's getting bigger. And if you're going to the right, it always goes through 0, 1.
Mhm.
And going to the right, it gets smaller. You see what's happening to the right? And going to the left, it gets bigger.
I see.
16/9 is like, it's still not 2, but it's close to 2. Now it's going up slowly. I don't like this example. They gave you a bad number. 3/4 isn't good. They should have given you 1/4. 1/4 would have been a much better one to see.
Yeah, because just with that part, it doesn't look very exponential.
No, it doesn't. But you know it's going to. You know what's going to happen is
Yeah.
it's going down here, and over here it's going like this eventually. But it's hard to see it just with those 5 dots. So I don't like that example. But you understand that it's still exponential,
Yeah.
right? All right. How about another one?
Let me flip through this math Excel here. Those are easy. Here's a word problem. Word problem. Save. Whoa. Okay, I just had a moment. This one. Okay. There you go.
All right. Write an exponential function to model the following situation. A population of that much grows that much in that much. How much will it be after that much? All right. So with these, here's always what you do. If it grows 4%, that means the rate is 1 plus 0.04. So the rate is 1.04. Remember that.
Yeah.
Okay. And this is your initial population. So let's call that A sub 0. So your formula, I think probably, what is it, like A equals A sub 0 times R to the T? That's the formula?
Something like that. Yeah. That's just a more simplified version of what we've been doing.
Yeah, that's essentially what you've got. So I don't know. If you want to tell me what your equation is, I'll write that in here. But basically, you're going to write 140,000. The rate is 1.04. Yeah, there you go. Oh, okay. So they're actually right. They have you write it in. Yeah. They have you write it like this. Usually you see it looking like this, but then you have to know that the whole rate, you have to add 1 to the rate. The rate is actually, 1.04.
Yeah.
Right?
I know that part though.
It's really growing at a rate of 104%. That's what's happening.
Okay.
Okay. So raised to the 14. Or to the T, which in this case is 14. Yep. So punch it in. 14, 1, 2, 3 times 1.04 raised to the 14. And that's the population. It almost doubled, which kind of makes sense. You want to know why it kind of makes sense?
Why?
the rule of sevens. So if the interest rate was 7%, here, let me just give you an example. Let's say 100 is what I started with, and the interest rate was 7%, so 1.07, then it's gonna roughly double in 7 years. And that didn't work. No, in 10 years. In 10 years? I thought it was a rule of sevens. Yeah, it roughly doubles in 10 years. I thought it roughly doubled in 7. I thought that was the rule of sevens. If you have a 7% interest rate, it will double in 7 years. But that obviously did not happen here.
Yeah, no.
I wonder if it would have worked for if I did continuous compounding, because this is just compounding once a year.
Yeah.
No, I don't think it would make that big of a difference. Anyway, now I gotta know. I gotta look it up. Hold on. Let's find out why the rule of sevens did not work. Maybe I'm confusing it with something else. Rule of sevens. Oh, rule of sevens in exponential growth. 72, that's what it is. It's the rule of 72, not the rule of sevens. I was getting it confused. What is the rule of 70? The rule of 70 is a way to estimate the time it takes to double a number based on its growth rate. Take the number 70 and divide it by the growth rate, and that tells you, yeah, so that makes sense. So 70 divided by 7 is 10 years. So it takes about 10 years to double it if it's a 7%.
I see.
So how long would it take to double? If it was 2%, it would take 35 years roughly to double if you were getting 2%. That's a pretty cool thing to know.
That is pretty cool.
You know what I'm saying? So like, look, if I took 100 and the interest was 2%, they're saying that in 35 years, it should just about double. Look at that.
Yeah.
How about that?
Huh.
So if your interest was 10%, then it should take how long?
7 years?
You are so smart. Let's find out
Yes,
if it's
sir.
true. Let's find out if it's true. Wow.
That's pretty close.
It was pretty close. So if your interest rate was 35%, how many years would it take to double?
2.
You are so smart. Again, 35 raised to the 2, this should be about double. Well, that's not quite double. Maybe it's not very accurate when you have that big, crazy big interest rate like that.
Yeah.
That was a little bit outrageous.
Not as
70
satisfying as the others.
That's right. It was definitely not as satisfying. All right. So did you get that one okay?
Yes.
All right. Do we have another one?
Yeah. I can. I think so. Go to the next question. What the heck? Oh wow, it's like the same question, except instead of 140,000, it's 130,000. What the heck?
I think you can handle that one.
Yeah. Wait, let me just go to the next one. Okay. Here's a big one. I mean, it looks big. I don't know if it's actually big. There's just a lot of writing.
Are we on page 4 or did you skip to a different page?
I'm on page 4 right now. What the heck? It didn't crop. That's annoying. Wait. Bruh. Just gonna do this. And then this. Assisted drawing tools. This. There we go. Okay. Okay.
All right. Suppose you deposit that much in the saving account that pays interest. All right. So this is that one formula. This is the formula. Amount equals the principal times 1 plus the rate over the number of compoundings raised to the number of compoundings times the number of years. But that's not what we've got here, because this is saying it only pays an annual interest rate. So have you seen this yet? I'm just going to erase those because your n is just
we
1
haven't
here.
we haven't
Your
done
n
it
is just 1.
Yeah, we haven't done this in class, but I was doing SAT practice the other day and it was talking about this and I had no idea what it was talking about.
It was talking about this or about compounding?
Compounding.
Yeah, so with compounding, this is your formula. And
Okay.
n is the number of compoundings per year. Number of compoundings, meaning how many times you take interest
Yeah.
per year. T is the number of years. R is
Okay.
the annual interest rate. P
How
is
is
the
that
original.
different? Wait a minute, how is that different from never mind.
So what's different is what we're doing right here, this example, is just talking about, there's your rate, but they're not talking about compounding it other than just once a year.
Yeah.
But they could, because banks don't pay you. Think about what a bank does. If you've ever looked at a bank account, if you've had interest bearing account,
Yeah.
they don't only pay you once a year, the interest, they pay you every month. So what they're doing is they're taking their annual rate and dividing it by the number of months, but then they're compounding that every month.
Okay.
So you're actually going to make more money if they compound it more often, because you're making interest on your interest. So the first month, let's say you had $100. Let me just give you an example of what I'm talking about with compounding interest. Let's say that your amount that you have in month 1, let's say that you have $100 in the bank, and let's say they're giving you a 10% rate, which is huge, but let's just say they're giving you a 10% interest rate. So the amount you're going to have in the bank in month 1 is $100, but in month 2, let's go year 1. In year 1, you're going to have $100 in the bank. In year 2, you're going to have $100 plus the $10 of interest. Right? In year 3, you're going to have $100 in the bank plus not just the extra $10, but you're going to get another 10% on that. So you're going to have an extra $1. You made $1 of interest on this $10. That's what compounding interest is. That makes sense? So in year 1, you made $10 of interest, but in year 2, you made $11 of interest, because you made your $10 on your original 100, but then there was an extra $10 in there. You made also 10% of that, which is $1. And then in year 4, you're going to make even more. In year 4, you're going to make, in your account, you're going to have 32.10. You're going to make an extra 10 cents. You made an extra $1, You made that $11, but then you made 10 cents on that extra dollar from the year before.
Mm-hmm.
And it's going to keep increasing like that.
Okay.
So you're actually, so that's the third year you made $12.10, if I'm doing the math right. The
Mm-hmm.
first year you made a $10 in interest. The second year you made $11 of interest. The third year you made $11.10 of interest.
Okay.
And it will continue like that every year. You're going to make you're going to make interest on the interest. Actually, maybe I didn't even do that right. I don't think I did that part of it right. I think this is wrong. So here's the formula. Let me just show you the formula. It's going to be your principal, which is 100, times 1.1 times the number of years. So if t equals 1, 100 times 1.1 raised to the first power, there's my 110.
Yeah.
Now I'm going to multiply that by 1.1 again. There's my 121. Now I'm going to multiply that by 1.1 again. There's my 133.
So it continues to add on to the previous amount?
Right.
Okay.
So what you've got is 100 times 1.1 raised to the third. That's your 133.1.
Okay.
So this was 133.1 because see yeah, that's why. Because I made 10% on $21 that third year. Right? Do you see how I have $21 of interest in my third year? So now I'm making interest. I'm not only making interest on my original 100, but I'm making interest on that extra $21. So that's 10 plus $2.01 and 10 cents. Sorry, $2.10.
Yeah.
So that's why I made $12.10 my third year in interest.
Okay.
See how it's going up, and it's going to keep going up every year. That's what compounding interest does. So look again at this formula. Your simple formula doesn't take the number of compoundings in. So now if we take that same concept and we say, oh, hey, let me say I'm going to give you 10%, but I'm going to pay every month. I'm going to compute your interest. Now watch what happens. So now we've got, is this making sense to you, what I'm saying?
Yeah.
Okay. So now let's do it monthly. If I'm compounding it monthly, this was annually, right?
Yeah.
Now I'm compounding it monthly. So if the amount I'm having in month one, let's say it's $100. In month two, so what I'm going to do is, this is your formula. Here, let me do this in green. So my formula is going to be this one. It's going to be 100 times 1 plus my interest rate, which is 0.1, but I'm dividing it by 12.
Yeah.
But I'm also, that's my rate. It's basically 1 plus 0.1 divided by 12. That's my rate. So let's do it. Let's see what that is. 0.1 divided by 12 is that number. So if I add 1 to it, okay, that's my increase every month is 0.0083 repeating. If I multiply that by 100, that's how much money I'll have in my bank account after month one. Okay. So after month one, I'm going to have $100.83 in my account. Okay. After month two, I'm going to multiply that number by 1.008. Oh, you know what? I should have stored. Here, let me clear this real quick. I'm going to store that for X.
Yeah.
Let's start over. I should have stored that for X. That would have been easier. 0.1 divided by 12. There's that number. I'm adding 1 to it because that's like my 100%, right? So I'm going to store that for X. Okay. So that's my rate. So if I take 100 times X, I'm going to get that number. If I multiply that by X again, this is month 2. That's month 2. So month 3, I guess. In month 3, my balance is going to be 101.67. See how I increased a little bit?
Yeah.
If I multiply that by X again, my rate, there's my month 4. And I can keep doing that all the way down to 12 months. How much money did I make if I wasn't compounding it annually? What did I make? I made $10, right? So look at what I'm going to make if I compound it every month. I will multiply this by X, but I will raise X to the 12th power. That's what I'm going to make. $110.47. So I made 47 cents more because every month I was compounding what I made the month before. The interest. Even though I wasn't making a ton of money. See, I was only making 83 cents here.
Yeah.
My first month, I only made 83 cents, and that doesn't seem like a big deal. And it's really not that big of a deal, but it is kind of a big deal if you, over time, because it's compounding. It's continually compounding. And so that number just keeps getting bigger and bigger and bigger. So I actually made 47 cents because I compounded it every month. The interest rate wasn't different. I just compounded it more often, and that's what this formula does for you.
Okay.
Now, you want to see the coolest thing?
It gets cooler?
It does, if you can believe it.
Wow.
The coolest part of this whole thing is there's a limit to the amount of compounding you can do. Because you might say, oh, you know what? Let's find the bank that compounds it like every second. If they're compounding it every second, this number isn't 12. That number is going to be like 1 million, right? But so is this number. It's also going to be 1 million.
Yeah.
So what you're doing is you're dividing 1.1 by 1 million. That's a tiny number, and you're compounding it a lot more, but it's really a tiny number. So there's a limit to what can happen. And that limit is this formula right here. PE to the RT. That's the limit to compounding. And I'm going to prove that to you.
Okay.
If I took this formula, 100, and I put in, whoops, it was a plus, 0.1 divided by, let's put in a huge number, 1, 2, 3, 4, 5, 6, 7, 7 zeros, okay? And I'm raising it to, this is just in 1 year, okay? So I'm going to raise it to 1, 2, 3, 4, 5, 6, 7. I'm raising it. That's the number of times I'm compounding it, but I divided it by that same number, right? Look at what this number is going to equal. Is it very much bigger than compounding it every month?
No.
It's not much at all. And check this out. See that PERT equation over there? 100 is my P. E is this button above the LN button. It's a number. E is a number. And R, remember R was 0.1, and my time was also 1. Watch this. You ready? You ready to be amazed?
What the heck? Wait, what?
That is the limit to the number of compoundings. That is called the continual compounding.
Yeah.
This is called continual compounding. You can make that N as big as you want. It will never get bigger than this number right here.
I see.
You see how that number's bigger? It might equal it or look like it equals it on your calculator, but it's not bigger than it. It's always going to be smaller than it.
Okay.
And I'm not going to prove why, but just trust me, that's true. And that's a pretty cool trick. It's a pretty cool thing to know.
Yeah,
So
I
that's
trust.
good. That's what you're going to learn next.
Okay. Huh. Interesting.
Yeah. Pretty cool stuff. I know math is pretty cool.
Yeah.
All right. Feeling good about it?
Yeah.
Well, hopefully that helps you when you tomorrow